Hello, everyone. This is Professor O. I'm going to give a lecture for the first lecture, actually, for the laser physics. So I have to give a brief introduction to the last lecture. It is combination of a very different areas of studies. Is electromagnetic waves, and then quantum mechanics, and also there are. If you go into details, then we have to think about the thermal physics. And also we should think about various types of laser medium. That means we have to be prepared for material scientific knowledge. Anyhow, let us start. Um, so what we are going to do is let me just move my, you know. So this is the lasers, and then you are going to follow the following contents. So absorption and emission. Absorption and emission is the very starting point of understanding lasers, because now absorption and emission they are regarded as a quantum mechanical process. And then we are going to move on to the two two different types of emission, which is stimulated emission and the spontaneous emission. Both of them are directly related with the laser, but stimulated emission is actually the light amplification by stimulated emission radiation. So that stimulated emission is directly related to the lasers. And then in order to have the stimulated emission, we need to build up the population inversion. And then we should think about what kind of optical gain. The gain means is the optical gain. And then this material should be put into some kind certain optical cavity. In this case, we are going to talk about Fabry-Perot resonators, and then we are going to think about what makes the laser lasing, so that this is the threshold conditions. So lasers is light amplification by stimulated emission radiations, and the lasing means this is the bulb, okay? And a laser has very noble qualities applicable to various applications, such as a monochromatic. That means is very I shouldn't say this really one single frequency, but it's very narrow frequency. And then it is highly directional with a low divergence, and it can be focused in a very small spot that allows us to do the many things, including the optical tweezers and material processing and the biomedical applications. And then it can produce short bursts of the light of very high intensity. And this is the subject of the two Nobel Prizes in recent years. So lasers, how it works. We have to think about quantum mechanics. So even though we are dealing with optics, then if we are to discuss lasers, we have to dig into the quantum mechanics. Simply because it's a stimulation of the electrons to higher energy level. Energy level means it's a quantum state. And then emission of the photon to go back to the lower energy state. The electron go back to the lower energy state, quantum state. And then due to this transition, the photon is generated. Okay. So photon and absorption and spontaneous emission, stimulated emission videos are shown here. So absorption. So here's the ground state in the incoming photons. By absorption, the electrons are moving up to the excited state. So absorption itself is a very quantum mechanical state, quantum mechanical phenomena. Okay. So photon goes on, photon disappears, and then electron is moved up to an excited state. And now let's try to think about the spontaneous emission. The electron wants to lower its energy and then goes down to ground state. And then by doing so, it emits a photon. That photon is spontaneous emission. And the stimulated emission requires specific two conditions. So first of all, you need to have electrons in the upper state. And then the photon should incident, and then this photon is multiplied, copied, okay, duplicated, and then that's the way of an amplification process. I need to go back. And the photon emission has two types, as we have seen for spontaneous emission. Spontaneous emission occurs spontaneously without any incident photon, but stimulated emission requires two conditions. One is there should be electrons in the upper state, and then there should be photon, which is resonant to this energy level, energy gap between the ground state and the first excited state. So this is the requirement for the stimulated emissions. So electrons in the excited state, that means you should have a larger number of electrons or higher population of electron in the excited states than the ground state, which is quite abnormal, which is not normal. In the thermal equilibrium, obviously the lower energy state is more densely populated than the upper state. But in the stimulated emission, it is reversed. So you need to have a high population in the excited state than the ground state. And then another requirement is that you should have a photon incoming whose energy on you is equal to the energy gap. So we say there's a resonant photon. And then by transition from the upper state to the lower state, and then it emits photon. But in this case, this photon is identical to the incoming photon. That means you have now one photon becomes two photon for these electrons. So if you have many, many electrons, then you have many, many identical photons. So now let's try to think about uh, stimulate versus spontaneous emission ratio. So stimulated emission rate is given by N2 B21 over rho F, N2 A21. So let me see. Hmm. I forgot to tell you what they are. Hmm. So here is the one, two state, and then population at the one state is designated N1 and N2. And then here is the photon, and the photon has a density of rho F. Okay. And then we have two transitions from 2 to 1. This which is related to P to 1. And then and B12. Then also we have a A21. So A21 is related to spontaneous emission. A21 is related to the stimulated emission. And B12 is absorption. Okay. So here is the case. Stimulated emission requires certain portion of the electron at the N2, where here comes N2, and existence of photon. And then it is related to this coefficient, transition rate B21. Okay. And the spontaneous emission does not require any photon, just need N2. Rho F is not needed. Okay. And then we get this N2, N2, and then eventually we get this one, and then this ratio is given by A21 over B21. So for black body radiation in thermal equilibrium, if it is in the thermal equilibrium, the rho F is given by Planck distribution, and A21 over B21 is given by this one. We are going to we are going to discuss this in detail later on, but let us try to see how this rate becomes. And then eventually it goes like this. 1 over exponential hc over lambda kt minus 1. So if it is lamp, if it is a lamp about whose temperature is about 1000 K, and then stimulated emission rate over spontaneous emission rate is given by this number, which is very small. That means stimulated emission in the classical black body is very, very small. That means spontaneous emission is dominant unless you do something else, which is the population inversion. So laser use is possible by stimulated emission, by uh, by increasing the population inversion. Okay? So in thermal equilibrium, we get two energy. There's E2, E1. And then density of atom is obviously, if it is in the thermal equilibrium, then the lower energy is preferred by this Boltzmann factor. Okay. So if it is higher energy, then it has a less density. And then if you go to the higher lower energy states, then it is more populated. Okay. But we call it optical pumping, such that electrons in the one state is now somehow electrons are moved up. And then we build this kind of a population inversion such that higher electrons are on the upper state than the ground state. And then we get stimulated emission. And in order to require that, it is also very important to note that this upper level should have a certain finite lifetime. That means the electrons goes up here, and it should stay there for some time. So usually about nanosecond to millisecond order. Okay. And then during those lifetime, then if you just pump the electrons from the level 1 to level 2 very fast, then you can build up the population inversion. Okay. So here is the absorption is given by L12 is given by N1, the electron at this one state, and then it is absorbed by existing photon, and then it is related with the transition rate constant B12. Okay, so in order to have a absorption, you need to have a photon, so that we need a photon density here. Spontaneous emission does not require any photon. It just, if you go to the N2, and then it just fall down by this H1. And stimulated emission requires certain number of population in the upper state and the existence of a photon and this transition rate. Okay. And then in order to have a efficient laser, we need a small N1. This should be small and N2 should be large. N2 should be large. And then we also require the photon density should be high. And this could be achieved by the optical pumping. And this is achieved by building a resonator for optical resonators. So that optical photon is moving back and forth. Okay. So requires a pumping, and in order to achieve the high population inversion and the high uh, 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 stimulated emission, you need a certain energy states. So most popular one is the 3-level and the 4-level system. Let's talk about this. So we have a 3-level means ground state, first excited, and the second excited state. So we are going to have its energy is E0, E1, E2. And the pumping is done by external photon. So remember, this is another photon. And then it is pushing the electron from the ground state to upper state to build up the population inversion. And then this will rapidly decay and then stay there. This is stay there, and then it has a certain long lifetime, so that you build up the electrons here. And then this 0 and 1, you achieve population inversion, and then if we have a photon, then you get the stimulated emission. Okay. So a good example of the 3-level system is Ruby lasers, is the solid state lasers. And the 4-level systems is a little bit different. It requires 4 distinctive quantum levels. And then once again, you require pumping that will move electron to the upper state, and then electrons will be transit to the lower state without any light, so that we call it non-radiative. So that means from here to here, probably it lacks the heat, okay? And then it goes down to this E2 level, and then you build up the electrons. And then it is making a stimulated emission between E2 and E1. Note that E1 is almost empty, and the ground state is mostly populated. But if you have this E1, that means it's even in a thermal equilibrium, this is very less populated. That means four-level system can have a very efficient way of making a build up the population inversion. Note that in the three-level system, there is always ground state electrons. It's not almost impossible to empty the ground state. It's not possible. There should be always a certain number of electrons. But in the case of a four-level system, this level is very, very empty, so that you can have a very high population inversion, and that means you can build up the high stimulated emission. So here is the case, helium-neon lasers. So helium atoms and neon atoms are shown. So helium-neon laser, because neon is the where the light is generated. So helium is receiving external energy, such as electrical discharge, and then it receives the energy, and then it transfers to the neon. So basically, helium ion atom does is that it transfer electrons to nearby neon atoms, okay? And then once you get these electrons here, it goes down to this transition, and then it relaxes down to here, and this will goes to this transition. So neon atom can emit the most well-known transition is here, 632.8 nanometer, which is the red. But in the same time, it can emit mid-infrared and infrared. Okay. So, in other words, what it means is that this level is partly empty. It's not a ground state, right? So that you have a helium neon laser is the typical example of a four-level system. And we have a very different types of laser, which is called semiconductor lasers. So we have a P-type and N-type. So once again, it's very, all of a sudden we are dealing with semiconductor physics. So we have a PN junction, and then in order to match the Fermi level, this energy band should be modified like this. So P-type conduction band, N-type conduction band somehow connected. Similarly, P-type balance band and N-type balance band should be somehow connected. So in this case, we have this kind of a intermediate state we call the depletion region. And then we inject electrons and inject the holes in here. And then electrons and holes are recombined. And that means electrons and holes are combined. That means electrons will fill in the whole. Okay, so it is the beta-basics of transition. Okay, very similar. And then it also requires a certain photon, and then if there is a resonant photon, then we can get the stimulated emission by population inversion. So in this case, we have a population inversion is built by carrier injection. That means we put the electron and put the holes at both sides. Okay, and then due to the nature of the material choice, we can have a high refractive index in the middle, and then we can confine the light like this. Okay, and that's the way to make a laser diode. Okay, so this is the first lecture, and then we are going to stop here. We are going to look into more detail of introduction of lasers, and then we are going to study bit by bit, more in detail, these characteristic equations first, and then we are going to do the simulation in MATLAB and also some laser CAD tools. Excuse me. Okay, so I'll be seeing you shortly in the classroom. Thank you.